we get into some of the more interesting probability problems today, as we're going to talk about kinds of problems you can do with what is normally known as Bayes' rule. Now, I am not going to get really fussy about telling you you have to use Bayes' rule on these problems. I think it's much easier in many cases. Here is Bayes' rule, but I think it's much easier if you do a tree diagram. And I'd like to show you how to do that. There's a couple different ways you can even do the tree diagram, but I think it is easier than adhering to Bayes' rule. All right, so in other words, if you have a group of 30 girls, 20 play softball and 10 do not. So what I'm going to do is, here are the softball players. There are 20 of them, okay? Here are the girls that do not play softball, and there are 10. Now, tree diagram. Of those who play softball here, 40% like math. 40% of 20 is 8. So 8 like math, and 12 do not like math. Agreed? Okay? And of those not playing softball, down here, 80% like math. So 80% of 10 is 8 like math, and 2 do not like math. Okay, that's filling out the tree diagram. Now, let's see if we can answer the question. What is the probability that someone who likes math? There are 8 here and 8 here. Okay, that's 16, right? What's the probability that they're a softball player? Well, these are the ones that are softball players. So out of the 16, we would have, for this one, 8, this 8, out of 16, which is 50%. Okay? What is the probability someone who is a softball player up here does not like math? It's 12 out of 20. 12 out of 20, which should be 60%. Okay? What is the probability someone who does not like math? Who are the people that don't like math? 2 here, 12 here, 14. What is the probability someone who does not like math is a softball player? 12 out of 14, and 12 divided by 14 is going to be 86%. Okay? Now, I just did it with events. How many are in each event? I want to now do it with probabilities. So, let's start again. And this is the way I think you ought to do your problems today in this section. All right, 20%, 20 girls out of 30 play softball. 20 out of 30 is roughly 67%. So let's make this 0.67 play softball, 0.33 do not play softball. Do it all in percentages. Of those who play softball, 40% like math. 0.40 like math. 0.60 do not like math. Okay? Of those not playing, 80%, 0.80 like math. 0.20 do not like math. Okay, now I want to answer the same questions and see if we get the same answer. The probability of someone who likes math is a softball player. First question. If somebody likes math, they're in this branch. To get to this branch, you had to first take 0.67, then you got to take it times 0.40. So it's 0.67 times 0.40 for those liking math. Down here, it is 0.33 times 0.80. Okay? What's the probability that they're a softball player? 0.67 times 0.40. Okay? So I'm going to do the top, and it is 0.67 times 0.40 equals, divided by parentheses, 0.67 times 0.40 plus 0.33 times 0.80, close your parentheses, and what do I get? I get 50%. Now, at first glance, you're probably looking here and saying, "Ooh, I don't want to do it that way, that's the hard way." Well, trust me, for what we get into, I don't think it is the hard way. All right. Next one, probability that someone who is a softball player, if you're a softball player, does not like math. If you're a softball player, what's the probability you don't like math? 60%. Right there, no work. This one, the probability someone who does not like math. Who does not like math? It's this branch, 0.67 times 0.60, see it? And down here, plus 0.33, 0.20, see it? What's the probability that they're a softball player? Not liking math is the 0.67 times 0.60. Do it again. 0.67 times 0.60 equals, divided by parentheses, 0.67 times 0.60 plus 0.33 times 0.20, close your parentheses, equals 86%. Same answers, okay? But we did it with probabilities, all right? Now, in spite of this looking a little more complicated, I think it is still the best way to do the problems. All right. Do the next one. We have, of a group of 1,000 people, 20% like art. I'm just going to do it with the percentages. 0.20 like art. 0.80 do not like art. Yes? Okay. Of the art lovers, 30% like burgers, 70% would not like burgers. Yeah. Down here, of the art haters, 80% like burgers, 20% do not like burgers. Yeah. Okay. Find a probability that a burger lover, stop right there. Burger lovers, this branch and this branch. Burger lovers would be burger lovers, 0.20 times 0.30 plus burger lovers, 0.80 times 0.80. Yeah? Okay? Burger lovers. Find a probability that a burger lover is an art lover. Where are the art lovers? Up there, the 0.20 times 0.30. Right? Okay? Do the math. 0.20 times 0.30 equals, divided by parentheses, 0.20 times 0.30 plus 0.8 times 0.8, close your parentheses. And what's the chance that a burger lover is an art lover? It's only about 9%. Okay? Next one's easy. Find the probability that an art hater, down here are the art haters, what's the probability they are a burger hater? No work. If you're an art hater, you're right here. What's the probability you don't like burgers? 20%. No work. Okay? Tree diagrams, I think, make this much, much easier, and stick with the percentages. Okay. This is an amazing problem. Be prepared, everybody, for a goosebump moment, serious goosebump moment, because you're going to be totally shocked as to what's going to happen here. Standard test for AIDS, HIV/AIDS is the ELIAS test. Test for the presence of AIDS antibodies. For every 1,000 people tested who do not have AIDS, 998 will test negative. They don't have AIDS. 2 will have a false positive. For every 1,000 people tested that have AIDS, 998 will test positive and 2 will have a false negative. Okay? Test is very, very accurate. It is estimated that 0.2% of college students have HIV. Let's start it out. Tree diagram. 0.2. Strike that. That's a percentage. 0.002 are the college students that have HIV. 0.998. Subtract that from 1. Okay, 0.998 do not have HIV. Okay? Now, they're going to take the AIDS test. Okay? They're going to take the AIDS test. When you take the test, it is very accurate. Okay? Those people that have AIDS, all right, the percentage that's going to test positive would be 0.998. Okay? So for people tested who have AIDS, 998 will test positive out of 1,000. That is 0.998 will test positive. 002 will have a false negative. How about the ones who don't have AIDS? Okay? For people that don't have AIDS, 0.998 will test negative. 0.002 will test positive. Okay? First question. What percent of people tested will test positive? Well, you can get positive results 2 ways. You can get a positive result here if you actually have AIDS, or you can get a positive result down there when it's a false positive. So what percent will test positive? It's either this branch, 0.002 times 0.998, plus down here, 0.998 times 0.002. Okay, that's the percentage that'll test positive. What is that? It is 0.002 times 0.998 plus 0.998 times 0.002, which is the same thing. And this is 0.003992. Not even a whole percentage should test positive. Okay? If a randomly selected student tests positive, if you test positive, you're going to be in this group. What is the chance that he or she actually has AIDS? The ones that have AIDS is right here. Yeah? The ones that have AIDS is here, so that goes on the top. Right? Okay? And if you take 0.002 times 0.998, get your answer, divide it by the ones that do, 0.03992 equals wow, that's incredible. I'm going to say that again. If a randomly selected student tests positive, what is the chance they have AIDS? 50-50. 50-50. That's incredible. This is one of the most accurate tests in the world. But if you test positive, it's only 50-50 likely you have it. Okay? Now, if a student tests negative, what is the chance that he or she does not have AIDS? You see, it's very interesting about this test. If you test positive, okay, what's the probability you actually have AIDS? It's only 50-50. Well, what's the first thing you're going to do if you test positive? Won't you go get another test, right? But what about negative? If a student tests negative, it could be extremely dangerous if that's only 50-50. Because if you test negative, you're going to say, woo, dodged a bullet, I'm good to go, man, right? But if it's 50-50, you're in trouble. Okay, you could potentially have it. We better check this out. If a student tests negative, how can you test negative? This branch, 0.002 times 0.002, or plus down here, testing negative, is 0.998 times 0.998. Okay? So if you test negative, what is the chance that he or she does not have AIDS? So this right here would go on the top, right? This branch will go on the top, 0.998 times 0.998 equals, divided by parentheses. This is what goes on the bottom, and it is 0.002 times 0.002 plus, and then this part where they test negative, 0.998 times 0.998, close your parentheses. If you test negative the first time on AIDS, what is the likelihood that you do not have AIDS? The likelihood that you don't have it is this, right? Woo! You're in great shape. You don't have to get retested if you test negative. It's extremely accurate. But the 50% is concerning, okay? The 50% is very concerning. If you test positive, obviously you should retest. If you test positive the second time, what is the probability you have AIDS? Okay, so where are the positive testers? The positive testers are here and here. Yeah? Okay, so I'm going to get rid of this. I'll let the 50% up there to remind us that that's after the first test. If you test positive up here, okay, these are the students that have AIDS, right? The test is very accurate. 0.998%, you're going to test positive again, okay? And 0.002 is the chance you'll test negative because the test is so accurate. Down here, if you test positive, down here, these are the people that don't have AIDS. Even if you test positive here, okay, the test is so accurate, 0.998, it's going to be a negative test the second time because you don't have AIDS. 0.002 will become a false positive if you don't have AIDS. Okay? Now, this is going to get a little cumbersome. See if I can squeeze this in here. So, the question is, if you test positive the second time, what's the probability that you actually have AIDS, that you're up here? So, how can you test positive the second time? This branch or that branch, right? Okay, so let's do it. 0.002 times 0.998 times 0.998 plus 0.998 times 0.002 squared, two of them. And on the top, what's the probability you actually have AIDS? It's this one on the top. Okay, now remember what this is. You're testing the second time. You've already tested positive. So let's do the math here. Okay. 0.002 times 0.998 times 0.998 equals, divided by parentheses, 0.002 times 0.998 squared plus 0.998 times 0.002 squared, close your parentheses, equals, if you test positive on the first test, it's only 50-50. If you test positive the second time, what's the probability you actually have AIDS? You're in trouble. You got it. Okay? It's an amazing, amazing problem in probability using the tree diagram. And what's the most amazing thing? If you test positive the first time, you're only 50-50 likely to have it. And you should get retested. Is this stuff great? Okay. Let's go on, try to find a better problem. Now, this is the way your problems look in the homework. A lot of them look this way. If you have a problem that looks like the chart, you can probably avoid making the tree. It's when you don't have a chart. If you just have a word problem with all the percentages mixed in, you should make a tree, okay? But if you have a chart, you can probably get away without it. Age 18 to 30 is 30% of all adults, okay? And out of this group, 12% of this group are homeowners, okay? And each group is like that. Of this age group is 25% of all adults. Out of this group, 23% of this group would be homeowners, and so on, so on. How are you going to find what percentage of all adults are homeowners? Okay? You'd have to multiply this times this, just like we did in the tree diagram. So it's going to be, for this question right here, it's going to be 0.30 times 0.12 plus, and you're going to have to add all of 0.25 times 0.23 and so on. So let's do it. It is 0.30 times 0.12 plus 0.25 times 0.23 plus 0.20 times 0.33 plus 0.25 times 0.44 equals, and I get 27% of all adults are homeowners, okay? What percent of all adults are 46 to 65 homeowners? Now, be very careful. This did not say what percentage of this group is homeowners. If it said that, like down here, what percent of adults 46 to 65 are homeowners? What percentage of this group are homeowners? That's easy, it's 33%. But it says what percent of all adults? What percent of all adults are homeowners? You've got to take the 0.33 times 0.20, and I get about 7% right here are homeowners, okay? What percent of these adults are homeowners? And we said that's easy. This one is 33%. A homeowner is selected at random. What's the probability that she is 31 to 45 years of age? We already got the answer up here. For all homeowners is 27%. That's our sample space. That's all the homeowners. What's the probability that she's in this age group? Well, what are the homeowners out of all the adults here? Isn't it 0.25 times 0.23? So 0.25 times 0.23 equals divided by 0.27, and I get 21% chance, okay? What percent of adults is older than 30? Well, that's easy. What percent of adults is older than 30? Just add those three up, 25, 20, and 25, 70%. Given an adult is over 35 years of age, what's the probability they do not own their own home? If you're over 65, you are in this group. You are already in this group, okay? We didn't say what's the probability of any adult. We said, what's the probability of someone in this group not being a homeowner? Well, it's 44% that they are. So to find the percentage that they're not, you simply subtract that from 1, and it should be 56%. Okay. Paragraph. Paragraph, what did I just say about a paragraph? Make a tree diagram, okay? We know that 54% of males, 0.54, use social media. Hang on. Our study, it will be 54% males. I got that wrong. Sorry. Our study is 54% males, 46% females. Yep. Okay. Out of the males, see, 21% of the males use it more than 2 hours a day. What's left out of 21? Is that not 79? 79% do not use social media more than 2 hours a day. Females, 37% use it more than 2 hours a day. Subtract from 100, that should be 63.63 do not use social media more than 2 hours a day. All right, problems. Person is selected from random. What's the probability that that person is on social media more than 2 hours a day? Okay, you could get it this way. You could get it this way. So I've got to take 0.54 times 0.21 plus 0.46 times 0.37. Let's do it. 0.54 times 0.21 plus 46 times 0.37 equals, I get about 28%. Person is selected randomly. What's the probability they're on social media more than 2 hours a day? 28%. You would think it's somewhere in between those two, right? And that's what we got, 28%. Okay. What's the probability that someone is on more than 2 hours given that it's a male? That's easy. If it's a male, probability they're on social media more than 2 hours is 21%, no work. Number 3, what's the probability someone is a female given that the person is on social media more than 2 hours? Here's the total sample space. This is all the people on social media more than 2 hours, 0.28. What's the probability they're a female? How did we get the female? Right there, 0.46 times 0.37, and divide. Equals divided by 0.28 equals probability it's a female is 61%. That makes perfect sense because the women are on social media more than men, right? You would guess the percentage would be higher that it's a female, okay? What's the probability someone is a male given that they're not on social media more than 2 hours a day? Okay, so we've got to start over. If someone is not on social media more than 2 hours a day, 0.54 times 0.79, see what I'm doing? Not on social media, 0.46, 0.63. That's your total sample space. That's all the people not on social media. What's the probability it's a male? Male, not on social media, 0.54 times 0.79. Let's do it. Equals divided by parentheses plus 0.46 times 0.63. Close your parentheses. Equals 60% probability. If they're not on social media, it's the guys who are not on. You would guess it'd be higher than 50-50. It is. It's 60% chance. Okay? Now, if it's 60% chance that it's a male, what's the probability it would have to be a female? It's got to be 40. No work. Ah, don't you just love the no work problems? Okay, homework. I've got one extra problem. Find the mean and the population. Remember, that's a sigma. Population, standard deviation, and change each one of the data to z-scores.